ID, the Future, a podcast about evolution and intelligent design.
Hello, I'm Tom Gilson. We're back again with Wesley J. Smith, Chair and Senior Fellow at the Discovery Institute's Center on Human Exceptionalism and host of the Humanize podcast. And we're in the second half of his interview with the co-authors of the 2022 book, Your Design Body. Steve Laufmann is a computer engineer, author, and engineering consultant with expertise in the design of enterprise-level systems. He's the founder of the Discovery Institute's Engineering Research Group, too. Howard Glicksman is a primary care and hospice physician with more than 40 years of experience in clinical practice. And just so you know who's who, the first person you will hear speak is Wesley Smith. Then Steve Laufmann's voice comes in very briefly as he turns it over to Howard Glicksman.
It's interesting. I mean, there was just, as we're recording this, a young man playing football, professional football, collapsed with a cardiac arrest on the field. And if your heart is stopped, I guess you're supposed, you can be called dead, but his heart was restarted. So why isn't that life restarting? Or was he never actually dead in that sense?
Well, I'll let Howard touch that one.
That's a Howard question.
I'm sure it is. Well, you can have a rhythm problem with your heart, ventricular dysrhythmia, that malignant ventricular dysrhythmia. So in certain settings that can cause that can be brought back. I mean, that's what we do.
In other words, because without getting into that young man, and we hope that he's all well.
Sure.
But when you restart somebody's heart and it succeeds and they remain alive, it's because they actually the life force, whatever that is, had never fully left. Is that right?
Yes. I mean, what you're talking about is what is death? I mean, what is the definition of death? And generally, it's usually a cardiopulmonary arrest. And really, the reason why you die if your heart or if your heart stops or your breathing stops, or they stop at the same time in general, separate from brain death, is because you're not getting any new supplies of oxygen. And then the cells in your brain die, and specifically the cells in your respiratory center, which tell you to breathe. And then it's sort of game over. Once those cells die, there's nothing to tell you to breathe anymore. And that's why in the old days, before we had cardiopulmonary resuscitation, et cetera, generally if someone stopped breathing or their heart stops, they would die. No one really knows when the soul leaves the body, but they were considered to be to die at that point. So in this case with this gentleman, they were able to get his heart back soon enough before he would hopefully have no or limited damage to the brain.
And in terms of reproduction, it always is life from life. So you have, let's say, in sexual intercourse and a conception, you have two cells that are alive but are not organisms,
right,
coming together and creating a life that is an organism. Is that right?
Exactly. And of course, the key thing for Darwinism is somehow you have to have the male and the female have to evolve at the same time. I mean, they have.
I never. Yes.
Yeah, their systems have to be in place. Besides the whole hormonal, the actual structures and the hormonal systems and release of the egg and the sperm, et cetera, they actually have to be in existence at the same time.
And so that they can interact together and have that conception take place. And even the simplest life form, a one-celled amoeba, as you said, it procreates by splitting. So that's life from life, correct?
Exactly. Right. Yeah. I think recently, I think it was the 200th anniversary of Louis Pasteur's his birth, I think. And, he was the one who approved abiogenesis. That he proved that abiogenesis was not true, because up until that time they thought that life could come from dirt, or they would leave things out in the open, and suddenly there would be flies or maggots or whatever. So he was the one who proved that only life comes from life. Now it seems like right after he did that, the Darwinism came along and said, "Oh, by the way, yeah, we got chemical evolution and abiogenesis, because that's the theory of abiogenesis."
So there's no example that we know of life spontaneously coming into being from non-life. Is that right?
That's correct. That's correct, yes.
All right. Let's talk a little bit about the medical side. you guys, and I'm sure Howard contributed this mostly, so I'll have Howard answer the question. On the medical side, you write that the body must, one, follow the rules. What do you mean by that?
So, yes, I think a good example is that what most people don't realize is, as Steve has alluded to, the laws of nature are trying to cause death all the time. So, for example, laws of motion, right? We all know that in order for something to move, this is the laws of nature, in order for something to move, you have to have enough energy to go against inertia, friction, and if it's going uphill, gravity. Okay, so for example, for your blood to move around your body, you have this innovation. You have to have a heart that pumps the blood around. All right, otherwise, the laws of nature are going to stop life from existing. So, also for a typical example is in the cell. There's these two forces of nature called diffusion and osmosis, but basically they control what happens with chemicals and fluid when there's two solutions separated by a membrane, and that's what you have in the example of a cell. The inside of the cell has a totally different chemical composition than the fluid outside the cell, and that has to be maintained. And you have something called sodium pumps that are using about 1/4 of your energy at any given moment just to maintain that function. So that's, again, following the rules. The life has to follow the rules, or actually combat the rules, come up with some sort of innovation to fight the natural laws of nature that are going to cause death. In fact, that's what happens. As I said, when you don't have oxygen, the sodium pumps in your cells no longer work. The cells lose their control of volume and chemical content, and they die. And when it happens in your respiratory center, your brain dies, and that's it. So that's what really happens.
And with trillions of cells, I've read somewhere that our cells are all replaced every 7 years, which is a completely different approach to procreation than an organism procreating. So the cells are actually recreating themselves as they're going through all of these various processes of following the rules. Is that right?
Exactly. Steve talks a lot about this as well. It's like the life cycle. For some reason, we don't really understand how certain bone cells, certain organ cells are always redeveloping or growing and multiplying, whereas other glands, the cells may stay a little longer. So, that your body changes. That's the whole point. You have totally different cells in the body, but you're the same person for some reason.
Yeah. Yeah. And I'm because of time, I'm going to just skip through the other three. Take control, must possess the exactly right functional capacities, which I think you've just described. And the body must be finely tuned, not finely tuned, correct?
Right. So that's what we're talking about. Like, if, for example, your temperature has to stay in a certain range. The oxygen level has to be a certain range. Your blood pressure, if your blood pressure is too high, you burst your blood vessels in the brain. If it's too low, you don't have enough blood flow to the body. And so your body is controlling the blood pressure, right? But it has to have some sort of set point somewhere deciding, what the blood pressure should be, as temperature, et cetera, et cetera. So,
and these are all happening at the same time, and for the most part, unconsciously, as far as we're concerned. We're not aware that is going on.
Yes, exactly. And until things go wrong, like you stand up
then
quickly
we know,
and you
my
feel
stomach
dizzy.
hurts. Yeah.
Or you stand up quickly and you feel dizzy, and that's a sign that the blood pressure's dropped too quickly, and the body compensates for that within a second or two. Yeah. I just want to comment also that the key thing in the book is that first part of the book that I do a lot of writing about is what's called homeostasis. Things that everything has to be just right. But then, of course, life is, we go on beyond that into, vision and hearing and balance and everything else that's, makes it great to be human. I mean, these are the sort of things that have to be going all the time without our control. I mean, because we don't have the capacity to figure it out all the time. How much water should I drink? How much oxygen should I take in? What should my temperature be? What am I going to do about it? If we don't have the ability to do that anyway, to manage it.
And I've noticed that, when I go to the doctor and he shows me the results of the blood test, if I'm within range, I guess you're saying I'm within that area of desirability. And if I'm out of range, then he will say, okay, I'm going to give you this to get you back in range, right? So that's how medicine works quite a bit.
Exactly. This is a very good point. I brought that up in another talk that, if we have all this lab work you get done and there's a normal range, well, where does that come from? And there's a reason why the normal range, it indicates that from our perspective, the body's working okay. It's like your car when they do the diagnostics on the car, or any other machine. And that's where a doctor will decide if it's appropriate, what to do, and the question is it affecting you or not? Yes, et cetera.
And Steve, on the engineering side, you say that, you treat the body, obviously you're talking about the human body, and as we said before, it could apply to other bodies, as a system. And you say systems require many parts.
Right. That's leading into our coherence principle. So you have just a control system. Let's take, since we were talking about respiration, you have a respiratory control system. All control systems have minimally 3 completely different parts. One is a sensor. The sensor has to sense the right thing, and it has to be sensitive around the set point, as Howard just described. So you have to know how much oxygen your brain is getting. So you have to have a sensor, and it has to sense oxygen in the blood, and it has to sense the right level. It has to know whether it's too much or too little. And then you need control logic. You need somewhere in your system, there has to be a decision tree of some kind, or a decision logic, which decides what to do. Oxygen's too low. I need to increase the blood pressure. The heart needs to beat faster. I need to close off supply to other parts of the body so we get more blood pressure to the brain, whatever the solution is. So that's the decision logic. And then you need those systems that affect the change. So you need systems that can generate more blood pressure. So you need sensors, you need control logic, you need and you need the effectors. So in your knee, you have 4 ligaments which hold your knee together, and they work like a 4-bar system. If your audience has mechanical engineers, they'll know a 4-bar system. That's what your car uses for steering. Fish's jaws are built with 4-bar mechanisms. Actually, some of them have much more complex mechanisms. But so you need multiple parts. Each part has to be made out of the right materials. Each part has to be the right shape and size with the right capacity. It has to be able to do just exactly what your body needs. So,
and you're saying, is that the coherence part that
yes,
it has to do with the body needs?
Yes. So, the only transparent tissue in your body just happens to be on the optical axis in your eyes. No one wants to look through your skin and see your spleen. It's not helpful.
It won't get the chicks, right? It won't get the girls.
Yeah. The only place you have enamel is on your teeth. Why?
That's very interesting. And then you also say, in terms of engineering, they must exhibit, and for systems, complex interdependencies.
Yes. And that's what Howard was talking about earlier. So you can't get oxygen to your cells without your cardiovascular system. Your cardiovascular system can't get oxygen without your lungs. So, and each of those.
And what came first, the chicken or the egg, right?
Yeah, that's exactly right. So there are, in the common vernacular, everything in the body is a chicken and egg problem.
And you need it all at the same time.
Yes,
that's right.
And if you have part of it but not the other part, that's one of the billion ways to die.
Exactly. So even the simplest single-celled bacteria has to solve 12 or 15 significant problems to be alive. And it has to solve another 12 or 15 problems to reproduce. So without...
and that's just a one-cell organism.
Exactly. And in the human body, there are thousands and thousands of things going on constantly to keep you alive.
At the same time. Is there anything about the body, because, we obviously have learned quite a bit over the last few hundred years. Is there anything about the body that remains a mystery?
So I'll answer that, and then Howard can correct me.
Correct.
So that's what he does. I would argue that we don't know very much at all about the human body. We don't even know how many proteins the human body can produce. We don't know where they're produced inside the cells. We don't know when they're produced. I mean, we can sometimes observe that they've been produced, but we don't know the control systems that are doing that work. We don't understand how medicine works to a large extent. We in other
words, when I take an aspirin because I have a headache, my headache goes away, but you don't know why my headache goes away?
Well, we may know why your headache goes away, but we don't know what causes cancer, and we don't know what makes cancer go away. So there are a lot of genetic variations, and there are so much that's just not known, which is why a lot of the detail we'd like to have put in our book is just stuff that's not known. We couldn't put it in because nobody knows.
All right, Howard, the cancer question. I always thought cancer was caused by cells being mutating and then kind of forming this tumor and so forth. We don't know why that occurs. And doesn't chemo kill particular types of cells and not other types?
I wish I could answer that better. I'm a hospice physician, but I think a lot of what you're saying is true. I think that a lot of the cancer research, though very interesting, a lot of the cancer research it relates to what's called connective tissue. That's a chapter we have in the book that you probably would not find anywhere else. How the cell actually interacts with the milieu in which it is. So how they determined that when you have pluripotent cells, when they start developing, if you change one cell into another milieu, it detects the connective tissue around it, and so it will develop. Like if you put it in like the background of a nervous tissue, it will become nerve tissue. If you put it back in bone, it will become bone. So this is all related to cancer research. So I did want to make a comment though when you asked about the body, etc. When you asked that question, I have to admit that I think as a physician we tend to have hubris, like, oh, we know so much, right?
Right.
But what I've learned from Steve is the humility of asking the question. Here's the basic question that Steve started asking when we started talking. Where is the body plan? Where is the system? We've got the zygote, but where is the three-dimensional system that explains where every cell is going to go, how big it's going to be, what the organs are going to look like, etc. Something I never thought about because engineers think of that way. So even when you asked the question, my reaction was like, yeah, we know a lot. Okay, there's a lot we don't know. But
so let me translate, because I was involved in the stem cell fight back in the 2000s. So when a egg and the sperm unite and there's fertilization, what results from that is a one-celled organism called a zygote. And within that one cell is the potential to create all of the differentiated kinds of tissues that we find in our body, of which, there are many, many, many. But that's all existing once that one cell organism comes into being. But we don't know we know what happens, like differentiation and so forth, but we don't know how. You're saying that one cell organism has within it all of that potential to create the complexity that you've just been describing. Is that right?
Exactly. That's exactly what, and you put it perfectly. And it's just amazing that one cell organism, all that information about that human, human being, it's all in there. And Steve's initial question, because he's an engineer, like, when people read this book, my perspective was, I'm hoping they're going to ask themselves, how does that really work? But on top of that, the Steve perspective is, how do you build that from the ground up? And over the last few years that Steve and I have worked on this, he keeps asking the question, where is this information? Where, nobody knows. Okay, now they talk about gene regulatory networks, et cetera, that may turn on this system or that system. And the key thing you're talking about is there's like over 200 different types of cells in the body, right? So as you say, differentiation. So you've got maybe people don't understand that every cell in the body, almost every cell in the body has the exact same DNA, but the beta cell in your pancreas, it uses the DNA to make insulin, and one of the ones maybe in your thyroid gland is going to make the thyroid hormone, but it still has the same DNA. So this is your point that you're bringing up. This is just so amazing that all these cells somehow differentiate. They become the tissue that they're going to be. And of course, once they do that, then they can't multiply, et cetera. So early on, though, they have that potential. This is the whole point about adult stem cells, et cetera. Yes.
You have a full chapter on allegations that the body is poorly designed as a means of rebutting the idea that there's an intelligent design. Why do you think these arguments ultimately fail?
I'm not sure if Steve's with us still or not. But
He's here.
To answer it. Okay. Did you want to answer that, Steve?
Yeah, I'll take a swing at it. So they usually fail because they're not serious. And they're not serious in the sense that biologists seem to be completely unaware that there's a whole engineering discipline associated with evaluating a design. And none of the bad design arguments that I've ever seen goes through any of the rigor that an engineer would deploy to evaluate a design.
So if you're going to evaluate a bridge, you're going to, the construction of a bridge, whether it was adequately constructed, will hold the truck, that kind of thing. You're going to go through a whole very rigorous approach to make sure that all the stresses work and so forth, correct?
That's
and
correct.
You're saying that doesn't happen when biologists look at the body.
That's correct. So they make typically one of 5 kinds of errors. And they either... So before you can evaluate a design, you have to understand the goals of the design. So one of my close friends worked on the mirror array for the James Webb Space Telescope.
Mm-hmm.
Designing the mirror wasn't really very hard. Evaluating the design, testing the design, and making sure the design would hold up against the stresses required for its launch and deployment took years. It took years, and that's and the level of detail, because they can't go fix it. If something goes wrong, it sort of had to work the first time. So the level of work that goes into evaluating and verifying a design is extraordinarily detailed. And so if you're gonna take a body system and critique it, you need to understand the design. Then you have to understand, this is probably the major one that people mess up on, is the second point is you need to understand what the design trade-offs are. I could make a car that would go 1 million miles an hour, but it can't have any mass.
Yeah.
So I can't carry any cargo.
And more practically speaking, as we've wanted to increase the miles per gallon, we've made the cars lighter, which makes them less safe for the occupants.
That's right. So there are all kinds of trade-offs. There's a reason that a tractor trailer can carry large loads and a Honda Civic cannot.
Yes.
They're designed for completely different uses, and they make very different trade-offs in the design space, in those degrees of freedom we talked about.
So as a matter of engineering, there's always going to be a trade-off of some sort.
That's right. So it's very hard to say that something, let me rephrase that. It's very easy to say something is suboptimal, but when you take a system as a whole, it's the notion of optimality sort of doesn't apply anymore. You optimize on certain design features based on what your goals are, and other design features you may sub-optimize because you have to in order to get the thing to work. So
the opponents of intelligent design would say, well, there was no design, so these things kind of came into place more or less by random events, and there was really no trade-off. And you're saying, no, there's always a trade-off to make something work the way it does. Is that right?
That's right. The forces of chemistry and physics require trade-offs for everything. To solve the problems that your body needs to solve in order to be alive, you have to make trade-offs.
If I could just add something, one of the sort of quote unquote tricks that's done here is basically the idea is to find something that people suffer from and say it wasn't it was badly designed, and then suddenly jump from there and say it wasn't designed at all, and then not try to explain how it came into existence in the first place, which is what our whole book is about. So in that chapter, as an example, we talk about the throat, pharynx, because you're at risk of choking, right?
Yeah.
And so we go through that extensively, but the trade-off, of course, is one of the couple of the critics say, well, if we could be like whales, they have a separate entry for swallowing and for breathing. Of course, the problem is we wouldn't be able to talk, and of course then that would make our whole language centers superfluous. I mean, they all have to be there at the same time. But they never mention that we should be whales, So it really is sort of humorous. As Steve says, I don't think they're very serious, but people do buy into it because if you really thought about it a little bit, you realize that they're.
So if we're designed by this great intelligence, and you don't try to identify what that is specifically, I mean, you're not promoting a Christian view or you are more or less a theistic view in a general sense. But if this great intelligence is the cause and design of our bodies, how come we wear out?
I don't know. Why do we die?
That's right. That's what I'm asking.
So this is the more serious part of the bad design argument, and that is degradation. Mm. One of the problems that the proponents of the bad design argument make is that, or one of the failures is that they don't account for degradation. Everything degrades. Your TV falls apart, your car falls apart, your lawnmower stops working. We know this. Eventually your roof starts leaking. Everything degrades over time. So how do you account for that in the history of life? Why do organisms die? I mean, maybe it's programmed, maybe it's degradation, maybe it's some combination. This is another thing that
maybe it's so that other organisms can live.
Yeah, we just don't understand. So this is another area where we just don't know enough yet.
And Darwinism, as we've described it, wouldn't actually account for that either, would it?
No.
That's very interesting. Final question, just about, or actually penultimate question. Does it really matter that whether we evolved, were created in the Christian sense, or were intelligently designed in some fashion? We are what we are. Why does it matter how we came to be what we are?
Well, we believe this is the probably the single most important question any person has to choose in their life. If you are the result of purely material processes that did not have you in mind, or the human body in mind, then you are essentially a cosmic accident. There's no purpose, there's no intention, there's no value, there's no inherent value. And that leads, if you believe that about yourself individually, that leads you to a very desperate place. It's a dark
lack of hope, isn't there?
Yeah. Mm-hmm. It's a worldview that leaves the individual with a sense of dread and despair and futileness. And the opposite answer leads in exactly the opposite direction. If our bodies were intended, then maybe we as individuals are intended, and that sort of opens up the possibilities. It leads us to a world filled with hope and the potential for purpose. And
which brings us to human exceptionalism, which deals with the intrinsic dignity of human life and the obligations we have as human beings simply because we're human beings. So throughout this whole interview, we end up, where my passion is, which is human exceptionalism.
If I can just add something, Wesley, to that, is that, and I'm sure Steve has felt this while we've been writing this project, the sheer beauty, right? This is what we're trying to pass on to people as well, okay? The sheer beauty of the body, or how everything works. I mean, people can look at a bridge, they can look at a building, they could look at a painting. Everyone can appreciate that. And I think what we want people to recognize and hopefully benefit from in their lives is the incredible beauty of how everything is working so well in the body. And at some level, we have to be motivated too. Why would I be bothered writing? And why am I writing this for 20 years, or Steve last 4 or 5 years? or like what you do about human exceptionalism. You're out there sticking your neck out and standing up for humanity, and there's something in our hearts. There's something deep in our hearts that is motivating us, and
maybe that's something that can't be measured.
Exactly, that's the crux of what's part of the book. But I think that binds the three of us together. Yes.
Yeah, and creativity. I mean, moral sense, creativity, things that really you cannot. An AI, I've had shows on AI. I mean, they're just following their programming. Human beings are different than that. Well, we're out of time. So what next for Stephen Laufmann and Howard Glicksman?
Well, so we, in this book, we introduce a theory of biological design. It's early times for this theory, but it has a lot of legs and it's got a lot of ways to run. So we are actively working on research on this new theory. So I'm going to go out on a limb and promise that at some point in the future, maybe even in my lifetime, there will be a second book, which is exploring this theory in much greater detail with backing it up with scientific research.
I think from our experience, I was just going to say, yeah, I'm just staying there with Steve, on his coattails, as my wife says. But I would hope that what we've written in this book will be it's sort of like a primer for engineers. So every engineer who sees where their specialty fits into something in the body, they'll recognize, hey, I can speak to that. I see how that fits into what I do, and will allow
so you would
more
like
research.
To have other people come and contribute to the research you're doing, and with regard to the biological engineering aspect.
Absolutely.
Yes,
and biological engineering, we're not talking about genetic engineering the body. You're talking about figuring out how it works.
Yeah, right. Reverse engineering the systems in the body, and that will give us great information about how the body came to be in the history of life. So part of our theory is that organic growth occurs, so that not necessarily things were created the way we see them today, but that things change over time, and we want to understand the forces behind those changes.
Well, this has been very interesting, and I look forward to your next book. And thanks for being with me. I appreciate it.
Yeah, thanks for having us.
Thanks, Wes. Appreciate it.
Thanks for listening to Humanize from Discovery Institute's Center on Human Exceptionalism, where human rights meet human responsibilities. Discover all the good work of the Center on Human Exceptionalism by visiting discovery.org/human. We can only do this work, speaking on behalf of human life, human thriving, and our exceptional place in this world and our cosmos, with your support. We invite you to make a one-time gift today and to consider starting a monthly gift to support the Center on Human Exceptionalism and this show. Wherever you're listening to Humanize, please take a moment to rate and review the show. You matter. Your actions matter. Be bold, be exceptional, and be back soon.
You've been listening to Wesley J. Smith, chair of the Discovery Institute's Center on Human Exceptionalism, talking with Steve Laufmann and Howard Glicksman about their book, Your Designed Body. We say thanks to Wesley Smith and the Humanize podcast for permission to rebroadcast. Be sure to check out Your Designed Body, available easily on all the major online booksellers. For ID the Future, I'm Tom Gilson. Thank you for listening.
Visit us at idthefuture.com and intelligentdesign.org. This program is copyright Discovery Institute and recorded by its Center for Science and Culture.